Hi, this is chapter 2 of the finite element class. In this case, we're going to be developing equations for 2D and 3D elasticity using finite elements and the principle of virtual work. Now, we'll save the theory of how finite element works mathematically for a later chapter. Right now, we're going to get down to the nitty-gritty of some practical applications. So we're going to start this chapter 2 by talking about finite elements for elasticity. So first of all, we have to state our problem. Okay, so we draw a potato, a generic elastic domain, and we're going to call that omega. And that domain is bounded by two types of boundaries. We're going to call this the essential boundary, and we're going to call that the natural boundary. And together, the essential and the natural boundary make up the complete boundary of the domain. So there's no other type of boundary, right? At each point inside the domain, we define, so this is a point with coordinates x, y, z in general. We're going to define the so-called displacement field. So u is going to be a vector function of space called the displacement field. All right, and at each point we're also going to define some other things. So we're going to define, let's use this color, a vector b of body forces. So we can already have some definitions. Omega is the solution domain. B is the body force vector function. So it's a function of space. And U is the displacement field. Okay, so the displacement field is a function of position in space and is a vector of x, y, and z components, all respectively possibly functions of space. That's our setup. This is basically our unknown, so that's what we want to solve for in an elasticity problem. So for example, we can have a beam. Our domain might be a beam, a box-shaped beam that's fixed in one end. This is the length of the beam, height of the beam, and its cross-section might be something like this, b times h, right? And you might want to have self-weight. So if you're subjecting this to self-weight, let's say you have an origin of the coordinate system x, y here, and at each point your b vector is actually going to be minus rho times g. That's your b vector. So you might want to write it out as follows. You might want to write it out to be b equals 0 minus rho g, where rho is your typical mass density and g is the gravitational acceleration. Cool. So that's part of our setup. And we want to solve for, in this case, for the displaced shape. So ux, uy, uz, in this case, if it's a planar shape, you're going to have something that looks maybe like this. It's going to be the displaced shape. And the displaced shape is given by the displacement field. Okay. So that's our setup. Now, moving on, we need to write the equations of equilibrium for this. So we're going to start with the strong form of the equilibrium equations. So the strong form of the equilibrium equations, well, this comes from mechanics of materials. So when you do force balance in each differential element, you'll get that the divergence of the stress vector is going to be equal to the force field. And you run this together with some other things. So first you need that sigma. So okay, in this case, this equation is not a function directly of u, our primary unknown. So in order to get that, we'll say sigma is equal to E times epsilon. That's our constitutive equation. And that's Hooke's law. And then about this, so this is the sigma is the stress tensor. And we're talking small deformations here. So it's the standard stress tensor you see in mechanical materials. It's not one of those advanced Piola-Kirchhoff or other more advanced formulations. Epsilon is the strain tensor. So it's given by the symmetrized strain tensor. So nabla U plus nabla U transposed. It's convenient here to write this in tensor notation. So in tensor notation, epsilon ij, or in index notation, would be 1/2 of dui to dxj, where xj is x1, x2, x3, xyz, duj partial over dxi. And you can further write this if you want to use really compact Einstein notation, I comma j, j comma I. Okay, so that's your strain tensor. Let me get my head out of the way. And the stress tensor, similarly, it goes through Hooke's law. So this is a tensor, this is a tensor contraction. So we're going to have sigma ij is going to be equal to ei jkl times epsilon kl, right? Where you have summation over the repeated indices. So here the indexes ij, kl will take values 1, 2, and 3, 2 in 3D, sorry, 2 in 2D, 3 in 3D. Let's see if I can get that into focus a little bit better. It's as good as it'll get. And so this particular form, so this is the general stress strain elasticity, stated in terms of tensors. Okay, from now on we're going to adopt what's so-called Voigt notation. Where we basically express all tensors as vectors. So we'll say sigma is the vector sigma xx, sigma yy, sigma zz, and tau xy, tau yz, tau xz. And the same for the strain tensor. Here we go, epsilon xx, epsilon yy, epsilon zz, gamma xy, gamma yz, gamma xz. So these gammas that I'm showing down there, those are actually twice the epsilons. So this guy over here would be twice epsilon xy, as given from this equation. Okay, that's the complete angle as opposed to half the angle. Okay, so we're stating elasticity in terms of different things. So we have a domain given by omega, And we distinguish two boundaries, the essential boundary and the natural boundary. We haven't talked too much about those till now. We identified the displacement field, and a short example of what that would look like. And then we're now moving into stating the equation that controls equilibrium. So that's going to be minus the divergence of the stress tensor is going to be equal to the body force vector. To that we add the constitutive equation, so the constitutive law, Hooke's law in this case. We'll write this down for a couple of cases, particular cases, 2D and 3D elasticity, in just a sec. But then the strain tensor is what has the displacement field inside, so that's what gets you over there. And we're adopting this void notation, so-called void notation. Okay, so we have in void notation, so we want to write this divergence vector, divergence operator. It's going to act on the tensor. So the way that looks like is nabla sigma. This gives you a vector, because the right hand side is a vector, right? So it's equal to the b's. But here what it does is, nabla is always, this nabla tensor is always going to be d dx, d dy, d dz. Here it's transposed. So the dot product with the, or the internal product with the strain tensor would give you something like d sigma xx over dx plus d tau xy dy plus d tau xz over dz. That's for the first component. Then you have let's do it correctly, d tau xy dx plus d sigma yy dy plus d tau yz dz. And let's do it, let's have it for completeness, d tau x z dx plus d tau, here we go, yz dy plus d tau, sorry, d sigma z over dz. So now that we were writing tensors in void notation, let's write down what the nabla operator would do. We'll call that the d operator. So we needed to do this. We'll say this equation becomes minus d transposed sigma. Okay, the transpose, you'll see clearly why it comes in a second, but it's going to be, so you need to have derivatives of these guys followed by derivatives of these guys. So you're going to need to have, so if this is a 6 times 1 vector, this guy's going to need to be, and on the result, which is b, right? So you have the 3 components, is a 3 times 1 vector. This guy, the d transpose, is going to need to be a 3 times 6 matrix. So let's write d transpose. Should give us something that looks like this. Okay, so let's do that. 3 down. So first we need the dx. So we're going to have a dx. Then we're going to need, so we can start saying it like this. So dx so here I'm going to have sigma x, sigma y, sigma z, tau xy, tau yz, tau xz. That's the order I adopted. So So that means if I need d dx, then this guy, I'm going to have 0 here, 0 here, and I'm going to have this guy, d dy, and then d dz, and I need another 0 here. Okay, there we go. Now I need xy, so I'm going to have d tau xy, this guy here, d dx, and I'm going to need d dy, and d dz is going to be over here, d to dz, fill the rest up with zeros, and finally I'm getting d dz, and then the other two involved is yz xz. So yz xe, this one is d dx, 0, d dz. Okay, so that's our d-transposed tensor. So that gives us that the d is just the verticalized or the transposed version of this. And from there on, here we go. So we get the strong form of the partial differential equation for elasticity. In this case, 3D elasticity would be minus d transposed sigma in void notation equals to b. B remains the same as before. Now in voids notation, we're going to have sigma equals e epsilon, where now these are matrix operations. So this is a matrix of elastic coefficients. This is the stress tensor in void notation, the strain tensor in void notation, so the ones I have back here, those are the ones, as opposed to these ones. And then I should write these relationships over here. We can just note from here that epsilon in this case is going to be d applied directly over u. So that's why we use the transpose over here, because now we can use it directly over here. Okay, you can check this out by doing the actual derivatives using this operator and transposing it and applying it directly to u. Let's see if you get the same. But now let's remember our domain. Shape doesn't matter. And I said we had two boundaries, so we have the essential boundary. On the essential boundary, this type of boundary is essential because the statics problem cannot be solved without the essential boundaries. You always need an essential boundary. Otherwise, it's going to lead to ill-posed problem. It's going to lead to a singular stiffness matrix. So this is essential boundary. Or essential boundary, and there you impose essential boundary conditions. And these are conditions of the form u x, y, z is equal to some fixed function, some known function, could be 0, for x, y, z in the essential boundary condition. See that I'm writing on top of me again, like this. So u x, y, z is going to be some known function of x, y, z, this known, usually 0, for all points in the essential boundary condition. And elsewhere, we have natural boundary conditions. So those natural boundary conditions might be applied force, applied tensions, for example, applied so-called tractions. So we have some tractions, T, and the way it works in the equations, you'll have the traction is a known vector function is equal to the stress tensor times the normal. And here I'm using, for a while, I'm just using the usual tensor notation. This would be the normal expressed in tensor notation, and sigma would be expressed as a matrix as a tensor, right? So the traction, the known function, is equal to this. So this, what bounds it together, puts everything together, and xyz in this case is in the essential boundary condition. Yeah, and if you have 0, that's fine, it's 0. You cannot have an empty, so this is still part of the essential boundary condition. The only thing there is that the sigma times n is equal to a traction vector is equal to 0, wherever you don't have any loads defined. You can safely ignore those, but mathematically those are part of the natural boundary conditions. So these are essential boundary, these are called natural boundaries. That's where you define the natural boundary conditions. So this is the setup of general linear 3D elasticity that we're going to use for the rest of the finite element, the rest of this month, the chapter 2. We're going to specialize this, so this form right here that I'm writing, this is a so-called strong form, because it's a strong statement of equilibrium. It's a pointwise statement of equilibrium using derivatives. In the next video, I'm going to show you the weak form, which is important for finite elements. The weak form of this partial differential equation, or the equilibrium stated in a weak sense. We're going to talk about what that weak sense means. But for now, spoiler alert, it's just using virtual work on top of this. As far as the physics go, the math is a bit deeper, but we'll talk about those later. Thank you. Till next video.